Alright, problem number 3 on homework number 1. Prove the empty set is a subset of any set, and we're actually going to prove it two different ways. The definition of what it means to be a subset, which is very important to have a definition. We need to assert that a set A is a subset of B if and only if for all elements X that are a member, or you can say an element of A, that X must also be an element of B. In other words, by definition, in order for A to be a subset of B, for every single item in A, that item must also be in B. That is the definition that we have. So even though these two things are equal, A is a subset of B, and B is a subset of A, because for every item in B, that item is also in A. And for now, we're just going to say that A is equal to this empty set. Now we're going to do a proof by contradiction, so we want to take the opposite of what we're claiming. Suppose that A is not a subset of B. By definition, that means that there exists some element X which is not a member of B, which means that there's something in here that is not in B. So to claim that there even exists an element at all in A, then that is a contradiction. To claim that there's anything inside of the empty set, it can no longer be the empty set. Therefore, thus, A is in fact a subset of B. And it's important to note that when we talk about B, B is, an abstract concept. It can be any set in the world. It could be the set of 1, 2, 3, the set of orange, apple, banana. It doesn't matter what the set is. This still holds regardless of what the sets we're talking about are, as long as A is the empty set. Another way to prove this is to say that, based on our definition, we know that A is a subset of B, if and only if for all element X, which are members of A, that element is a member of B. Really just copying what we have right here. And because A is the empty set, we can state that for all elements X that are members of A, X is in fact a member of B. Because essentially there are no elements to check. I mean, the idea is so obvious that it's a little bit confusing just to say, okay, we're going to check everything inside of here and see if that is in our, set B. But the fact is, there's nothing to check at all. So it is true that for everything that's inside of A, that's going to be inside of B, no matter what B is, because there's nothing in here to actually check that it's also inside of whatever B might be. As such, we can say that this argument holds vacuously.